Okay, guys. So let's start it. Get started. So today I will give a talk about approximate DNA storage with high robustness and density for images. I'm Bingzhe from University of Texas at Dallas. So we already have 3 talks, and they have really great talks. So hopefully for this talk, I may introduce some different perspective of the DNA storage. Okay, so let's get started. First of all, we are living in the big data era. As the computation capabilities is significantly increased, there's a lot of emerging applications like autonomous driving, wearable devices, cloud computing, social media, and so on and so forth. All those emerging applications are generating a huge amount of data every day. So for those huge amount of data, we do need to have some storage devices to store that, right? So here is one figure to indicate how much data we have in the world. The International Data Corporation predict. So in 2020, we have about 44 zettabytes data in the world. And 5 years later, actually 2 years later, in 2025, the total amount of data in the world will reach 175 zettabytes. So with such amount of data, we do need to process all those data, and also we need to store all those data. We do have a different type of storage devices like hard disk drive, solid state drive, tape, and so on and so forth. But why we want to have DNA storage? Why we want to use DNA storage to store those data? So here is there one figure to indicate the different trend of the digital universe and the in-store capacity. So based on this figure, you can see after probably around 2030, the gap between these two curves become larger and larger. So in other words, the in-store capacity cannot catch up with the increase of digital universe. So people are looking for some new or emerging storage medium to store those large amount of data. This is one example. For example, if we want to store 200 petabyte data, and traditionally, if we want to store those data in the hard disk drive, based on the simple calculation, okay, we may have let's assume we have 8 terabytes hard disk drive, and based on the simple calculation, we can have about 25,000 hard disk drive to store this 200 petabyte data. And normally, the hard disk drive vendor can guarantee for 5 to 10 years lifetime of drive, right? So the bottom here give you one example of the 1 year bytes data center at Texas with areas of 715,000 square feet. So how about store this data to the DNA storage? So theoretically, we only need 1 gram DNA to store 200 petabyte data, and also the DNA storage can be preserved for more than hundreds of years. So based on these simple examples, we can see the great potentials of DNA storage. One is a high area density, the other is a really long persistency. I think previous presenters already covered the basics of the basic background of DNA storage. Let me quickly go through the process of DNA storage. So what is a DNA storage? We have 4 types of nucleotides in DNA, A, T, G, C. So for the DNA storage, first of all, we want to write the data into the DNA, right? So we have the binary data, and for the process of the write, we have encoding. We want to encode the data binary to the nucleotides, ATGC sequence. And then we need to assemble some metadata or primers, and then do the synthesis, which convert into the physical domain. So normally we have the DNA string length about 115 to 300 bases. Of course, based on different technology, we may have longer DNA string length. So for the reversed operation of the read operation, so basically we do need to have the sequencing process and do the disassembling, try to extract the payload information. And then we have the decoding back to the binary data. So this is the basic operations of the DNA storage with read and write. But in current stage, DNA storage is not commercialized yet because of DNA storage have a lot of issues. For example, DNA storage is error prone, it's very expensive, it's really slow, needs special preservation, some special technologies or the materials, and also may have really low encoding densities. So for example, for the errors of the DNS storage, some patterns may increase error rate. So if we have so-called consecutive identical nucleotides, long homopolymer like AAAA patterns, so it's increase the difficulties of doing synthesis or sequencing process. And also if we have like hairpin structure or secondary structure inside of the strings, it's also increase the difficulties of sequencing and synthesis. So in summary, so there are three types of the errors in the DNS storage: substitution error, deletion error, and insertion error. So I won't go to the details, but it's really straightforward. For example, the substitution error is if we originally have A, but when we read data out, it may change to G, right? So then we do need to have some ECC or error correction code or maybe read Cinnamon to recover those data. So due to this kind of errors, there's one special scenarios in the storage, so-called error propagation. So for this example, if we have like binary data, first of all, and then based on the encoding scheme on the right table here, so we can simply encode data 00 to A, 01 to T, and so on and so forth. And then we convert the binary data into the DNA sequence, right? And because the synthesis sequencing process is error prone, so we assume there's one error happens, one deletion error happens. That means for the second chunk here, C cannot be read out. Okay, then what is the sequence result? So we don't have C anymore. That means subsequent nucleotides will be shifted one nucleotide left. And then we decode the data back. So for the decoded binary, based on the example here, we can see only the first byte data is correct, but the all rest of the data is incorrect. That means one nucleotide error causes a series of the errors in its subsequence. So this is so-called error propagations. And also this is another example for the error propagation in sequencing process. I think Daniel mentioned that before. So sometimes we do need to read multiple copies out and then go through the voting scheme or maybe consensus process and then find out one final sequence. So here are some experimental results based on one paper on the bottom, and also we do some simulations. So basically the idea here is like even we have voting scheme or consensus process, so the error rate is kind of increased as the nucleotide position increase. So for example, if we look at here, so at the very beginning of these strings, so normally it has really low error rate, but when we increasing the nucleotide number or the position number, the error rate is become larger and larger because we do have insertion deletion error, and then some of the pattern will shift, and then it causes so-called error propagation. So this is a similar conclusion as the previous examples. And also DNS storage have another problem. So we expected DNS storage had really large capacity, but the DNS storage practical capacity is not large enough as expected. So this one is based on the random access one. That means we do need to have some primer as an indicator to random access all those data. So because of two reasons. One is the number of the available primer is limited because of the primer collision. Secondly, the number of available primer will be decreased when increasing payload size, which is about primer payload collisions. So here is some simulation result you can see. So I think we do have, okay. So if we just increase the tube size or the payload data size, and also we find what is available number of the primers. So basically the number of available primer decreased with the payload size increased, and the correspond is the practical tube size. So based on the simulation results, the practical tube capacity is about 145 gigabytes. This is another simulation result. So we assume there's no collisions, and also we assume there's some collision happen. And then based on the result here, we can see there's 5 times difference between two curves. So based on this simulation result, you can see the DNS storage capacity or practical capacity is not as large as you expected. Okay, so due to these two scenarios or the issues of DNS storage, so in this talk, I would like to cover 3 papers we have conducted before. So one is about image DNA, which solves the kind of increased robustness of the DNS storage, and DPDNA, which is trying to increase the encoding densities of DNS storage to increase the practical tube capacity. And the last one, HLDNA, is considered both increased robustness and also encoding densities of DNS storage. Okay, so let's go to the first one, which is about DPDNA, try to increase the density of DNS storage. So this is one typical encoding schemes proposed by, I think, 2016. So-called rotation code. So the key idea for this rotation code is, first of all, we do have binary data. And then we can use Huffman code, encode data from binary to base 3, which means we have 0, 1, 2 sequence. And then we can, based on the rotation code, so like write table there to encode data base 3 to the nucleotides. So the key ideas of the rotation code is, let me give you one example. For example, if we have the current ternary pattern 0, and then we know the last nucleotide is A, then we just encode 0 to C. So it's totally based on the previous nucleotide and also the current base 3 ternary patterns. So the reason people want to use the rotation code is it's kind of avoid the long homopolymer, because based on the rotation, we don't have any consecutive identical nucleotides anymore in this type of encoding. So it's decreased the difficulties of synthesis and sequencing process potentially. And also it's kind of maintain the GC contents roughly around 14% to 16%, which is really good for synthesis and sequencing process. But for this work or this type of encoding, it has low encoding densities. So based on the simple calculation, you can see it's mapping 8 bits to 5 or 6 tries base 3. It has around like 1.57 bits per nucleotide. But theoretically, encoding density is 2 bits per nucleotide, right? Or there's one paper mentioned about like 1.98 bits per nucleotide based on some theoretical analysis, try to avoid some bioconstraints, but it has some limitations as well. So if you look at these two numbers, 1.7 bits and also 2 bits per nucleotide, there's a really large gap between these two encoding densities. So we try to mitigate these issues by this work. Okay. So then we propose one code, so-called 2-bit code. Okay, so we just do a simple revisions on this previous rotation code. So we have like binary pattern, which is 0001, 1011, and also we also based on the last nucleotides. And then we just form this kind of the table to encode the data. So we call it 2-bit code. But for this type of code, it has problems of like if we have 11111 for 2-bit code, it will generate long homopolymer or really long consecutive identical nucleotides. For example, if we have the last nucleotide A and then we have a sequence of 1111, so that means we will generate 11111. That means we cannot avoid long homopolymers. And then we do a revisions on this one. So we just change the last columns from encode 11 into the 2 nucleotides. So that means we encode the 11 to AC, TG, CT, and G based on the previous or last nucleotides. So based on that, we can see we can avoid the long homopolymer. So we only generate like 2 A's or 2 T's at most, right? Because of this type of encoding schemes. But based on even for the 11 code, it still have some issues. So on average, encoding density is 1.6 bit per nucleotide, which is better, a little bit better than the previous work, 1.57 bit per nucleotide. But for some extreme case, if we have a sequence of 1111 like this way, with A at the beginning of the last nucleotides, and then what is the encoding density? So based on the simple calculation here, if we have all ones, first of all, we have A and AC, 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 AC. That means we always go to the last column, and the encoding density will be 1 bit per nucleotide. So this is kind of the lower bound of this encoding scheme, which has 1 bit per nucleotide. That is much lower than the previous work, right? And then we try to mitigate the problems or try to increase the encoding densities. And here is some observation to solve the issues. So if we look at some different type of data, and then we try to find the pattern distributions among of all those data. So for example, if we look at one image and at 300 bits, and this is a kind of the distribution, pattern distributions among like 00011011, and you can see all those 4 patterns are not same, or they have different distributions. And distribution actually kind of have a huge difference. So based on that, we think about if we can find the least pattern within one nucleotide or DNA, like a sequence, then we can just encode this DNA strings with 1 nucleotide per bit. And then the lower bound case will reach to or increase to like 1.6%. Or the lower bound case will be 25% for all patterns, because the worst case is like 25, 25, 25, 25%. And then we just encode randomly pick out one as a 1 bit per nucleotide. Others will be the 2 bits per nucleotide. On average, the encoding density will be 1.6. So here is kind of the process. How do we apply the digital pattern aware code? So first of all, we try to find the lowest frequency pattern and then use the corresponding code. So for example, if we have AA has the lowest frequency in a binary sequence, then we try to use 1-1 code. The 1-1 code means we do have the last column with the encoding densities of 1 bit per nucleotide, but for others, we'll have 2 bits per nucleotide. And by doing that, the worst case analysis is about all patterns evenly show in a sequence. And then the encoding density or the lower bound of this code is about 1.6 bit per nucleotide, which is for sure larger than 1.57 bit per nucleotide. So it's kind of a little bit increased, but for some biased sequence, we may have much better encoding densities. And also, we try to further increase the encoding densities by adding 2 bits code and also using variable length. So the key idea here is like, because 2-bit code can provide the ideal or optimal encoding densities, right? So, but the problems of not using the 2-bit code is it may generate long homopolymer or some other like issues which have the bioconstraint or violations. And then it's increase the difficulties of synthesis in sequencing or increase the error rate. But if we found some sequences encoded with 2-bit code with no bioconstraint violation, then we can encode this type of sequences with 2-bit code, right? So then we can increase the encoding density. And also for the variable length, the ideal case, we want to achieve the ideal encoding density, 2 bits per nucleotide. And this is one example. For example, if we just encode one sequence with 2 bits per nucleotide, and then find out, okay, for the last part of the encoded data has bioconstraint violations. So how about we just get rid of this bioconstraint violation, and then we can simply use the 2-bit code to encode the data to achieve the 2 bits per nucleotide encoding density. So here, of course, we do need to follow some conditions to make sure by using the 2-bit code, we can achieve the higher encoding density overall, okay? And here is the overall design. So there's 2 passes. So first pass is on the left side, which try to decide whether we want to use 2-bit code and also whether we want to use variable length in the DNA storage. And for the second pass, we do have the list pattern scanning process, which try to determine which code we want to use. For example, 00 is a list 1, then we just list frequent 1, we just use the 00 code and so on and so forth. And also we do have overall encoding density comparator. So either we use a 2-bit code or maybe 00 code or 01 code and so on and so forth. And the right side here is just give you the process of the encoding process. So one thing I want to emphasize here is we do have an encoding field to indicate which type of encoding scheme we are using for this DNA strings, because we do need to have an indicator to indicate this DNA strings use like 1-1 code or 2-bit code, And during the decoding process or the sequencing process, read process, we can recover the data back from the nucleotide to the binary data. And this one is the experimental result we have. So we test different types of data, web, database, text, image, videos. And based on the result here, roughly, we achieved the highest encoding density. For some of the cases, we can close to like 2 bits per nucleotide, which is really good. Okay, so let's move to the next one, which is about image DNA, try to increase the robustness of the DNA storage for images. So before that, so here is the motivations of why we want to focus on images. So for example, for the Twitter, it's handled about 3,000 images, or Facebook or Meta. So users are uploading about 350 million new photos each day. So you can see there's a huge demand for storing images. And here is the basic background of the JPEG-based images. So in general, we do have one JPEG images, and then we split the images into the 8x8 block pixels. And then in each pixel, in each block, we do have DC and AC coefficients. And then we do go through a series of transformations like DCT, condensation, DPCM, zigzag, and so on and so forth, and then convert data into the GIF format. So based on the basic process of the JPEG-based images, we have two observations. One is, in general, the images is kind of fault tolerance. That means if we have several pixels crashed in the images, and we still can recognize what the images is, right? So if there's a tiger in the images, even though several pixels are crashed, but we still can recognize these images are containing a tiger. Secondly, the DC-AC coefficients have different influence on the qualities of images. So based on this encoding process, we know the DC coefficients is kind of more sensitive to the errors compared to the AC coefficients. So based on these two observations, so this is our paper's contributions. So we propose an image-based DNA architecture, story architecture, and also we did AC-DC coefficient separation at DNA level because DNA has, the natures of DNA has the physical separations. And then we're adding barriers and also use the asymmetric barriers for the AC-DC coefficients. So later I will cover a little bit details about barriers and also the asymmetric barriers for AC-DC coefficients. So here is the basic process of the image DNA. So first of all, we do have the AC-DC separation because during the encoding process, we can store the AC and DC coefficient into the different DNA strings, right? So DNA strings physically are separated, So we can, based on this physical separation, to separate AC-DC coefficients as well. And then we go through the encoding scheme, maybe the rotation code, and then encode into the ATGC pattern. And also we try to introduce some barriers into the DNA strings, try to prevent so-called error propagation introduced before. Okay, later we will see why we want to introduce barriers into this one. And then we do chunking and assembling associated with like primers or indexing or ECC codes within the DNA strings. So here is the ideas of adding barriers and also the symmetric barriers. So because based on the rotation code we introduced before, so the rotation code can guarantee there's no two consecutive identical A's. So we try to use A as a barriers to keep the error propagation within a partition. So for example, if we have a DNA strings and then error propagation happens, but if we find there's one like barrier indicator AA in this sequence, and then we can restart the whole decoding process so that we can prevent the error propagation scenarios. Okay, and also the probabilities of generating AA caused by error is kind of low. So it's possible that with the substitution error or insertion error, we may generate some AAs, but the probabilities of generating this kind of AA is low. And also we use barrier window to preventing the errors of insertion and deletion and to further like increase the recoverabilities of the storage. Okay, so for example, based on the barrier window here, so we assume if there's one AA outside of this barrier window, we just regard that as regular arrows. So if there AA inside of the barrier window, we just look at that or regard that as a barrier indicator so that we can use barrier indicator to restart the whole decoding process. So another thing is about asymmetric barriers for the AC-DC coefficient. So based on the previous observation, we know DC coefficient is more sensitive to the errors. So then from the qualities of the images perspective, we try to increase the number of barriers in DC coefficient in strings. And also because we know the number of AC is much more than the DC. So from the overhead perspective, we try to reduce the number of barriers in AC DNS strings. Okay, so by doing that, we can increase the qualities of images, but also we can maintain a reasonable overhead by injecting the AA barriers into the DNS storage. So here is about experimental result. So we use the dataset ImageNet for the testing purpose, and we have two baselines, raw DNA and also the approximate image or IMG. So approximate IMG is based on the traditional approximation of the storage system, like a solid state drive, how they apply the software level approximation to solve this kind of error problems. And also the image DNA is a proposed work of our proposed work. And we use the metric SSM to evaluate the qualities of images, and the string length use about 215 base pairs. And let's look at the result here. So we inject different error rate, like from 0.1% to 2%. And based on the result here, we can see, of course, the SSM value is higher, the qualities of images is better. And based on the result, we can see our proposed image DNA always achieve the best, the highest SSM value. That means we achieve the best qualities of images. And here are the graphic views of images with different encoding schemes. So based on this example here, we can see our proposed image DNA achieve quite similar graphic views as the original one, but for other two baselines. So there's a result of really vague. And more results, if you have interest, you can go to the paper to find more results. Okay, so let's go to the last one, which is about the HLDNA, try to increase the robustness and density of DNS storage for images. So the motivation of this work is because images are error tolerant and DNS storage is error prone, so we try to combine these two together or consider them together, okay? So based on the previous rotation code, here is the one so-called lossless code design we proposed. So we may just have kind of this rotation manner, but it's still based on, okay, so this is the previous work, so based on the traditional rotation code. And now we propose kind of a new encoding schemes. We split the encoding into two areas. One is so-called high density area, the other is a low density area. But based on that, we can avoid long homopolymers, okay? So based on lossless code design, the high density areas has encoding densities of 2 bits per nucleotide, but the low density area is about 1 bit per nucleotide. So, but it's based on this lossless encoding scheme, we found, okay, so for the C0 or the C1 coding manner, so they have the same first bit, and also they do have the common first nucleotides, like the TC, TG, or GA, GC, and so on and so forth. Then the idea here is like, we try to increase the encoding density. We can combine these two rows together. So what it looks like here? Okay, so then we try to combine the low density areas into one row here. So then we have like 4 types of encoding schemes, but we all can encode 2 bits into one nucleotide. Okay, so by doing that, based on this encoding scheme, we can see we can achieve 2 bits per nucleotide all the time. But it may introduce some other stuff because there's no free lunch. In this case, we introduce some errors purposely. So for this example, we have 1x0 indicate 11 and 10 are both encoding into the same nucleotides. but will decode it back to 10. That means during the decoding process, we may introduce some errors. But this is kind of trade-off between the error read and also the encoding density. Okay? And also, we borrow the ideas of the image DNA to apply the barriers into these schemes. But here we propose some new stuff. So based on the barriers, we can use different encoding schemes before and after the barriers. So that means we may have the code 1 or encoding scheme 1 for this part, and then after encoding, after the barriers, we can use another type of encoding. So that means for one DN strings, we can use 2 types of encoding or 3 types of encoding scheme to increase the encoding density. And here are the overall designs of HLDNA. So the encoding, the first step is encode the binary to nucleotides based on the encoding schemes. So based on the density lossy to select which encoding is used. So we propose like 6 encoding schemes, and then based on, there's a trade-off between the error and also the encoding density. So following some equations in the algorithm there, so we just select one encoding scheme for this, maybe the partition or this DN strings, okay? Secondly, we insert the barriers to the DN sequence, and then adding the corresponding metadata like the primer, index or ECC, and so on and so forth. And the fourth one is the coding format to indicate multiple encoding in the DN strings. So for here, we do have the coding format to indicate, this is kind of combinations of coding because it's possible we have 2 types of encoding in these DN strings. Okay, so ATC may means the first encoding scheme we use like a C0 and second one use a C1 and so on and so forth. This is why we introduce 3 nucleotides for the coding format. And here is experimental result. Similarly, we use the image net, and for baselines we use the church and organics and also the blood words and also our purple schemes. And the metrics we use, one is the encoding density, another one is the SSM value introduced before. And here we use the DN string length about 300 base pair. So here is the overall encoding density comparisons. So there's 2 metrics, metric traits. One is the encoding density. So based on the result here, our scheme achieved like 1.923, which is close to the 2 bits per nucleotide. And of course, this is trade-off. So we sacrifice some SSM value. That means we purposely introduce some errors in the encoding schemes. But we can kind of increase the robustness of the DN storage system. So because we introduce the barriers and also use different encoding schemes for single DN strings. So if we purposely introduce some errors into the DN strings and then compare to others, our work appears the higher robustness compared to other baselines. And here is the graphic views of the images with different encoding scheme under the 0.5 error rate injections. Okay, so this is kind of the third work we have working on. And here is some potential DN storage researchers. So maybe in the future and also in current stage, our group is working on. So first of all, the scalabilities, because so far we still focus on the one single tube DN storage. But in general, because with the data become larger and larger, we may need multiple, maybe thousands or millions of tubes, right? And then it's a problem of the scalabilities of DN storage. So how do we access all those data based on the number of tube number or some other index information? So this is kind of the new areas we need to consider for indexing data in a large-scale DN storage system. The second one is the capabilities and also the encoding scheme and ECC. So here in this 3 works, we didn't introduce the ECC code. We just assume we simply use the reassignment code to recover the errors. But is there any new like error correction code can increase the robustness of DN storage? So there are some other works like LDPC code to like protect the DN storage. So what is a good ECC code for DN storage? And also the microfluidic system. I think the previous talk about microfluidic system as well. So more issues in the storage system are DNS storage, like DNS storage preservation, the issues of limited read number, because for each read we may consume maybe one droplet or maybe consume some of the DNA in the DNS storage system, right? So maybe we have the issues of limited read number and also the performance of sequencing synthesis or API to the user. From the system, a Linux file system perspective, how do we design the interface to the user by using the DNS storage system? Here are the conclusions of my talk. So first of all, I introduced three basic works. One is for the increasing array density. The other is the robustness architecture of DNS storage for images. And the third one is a hybrid lossless encoding schemes to do the trade-off between the error and also the encoding density. And also I introduced the potential DNS storage research directions. So here's the acknowledgement. So my collaborators and also the NSF, our lab is funded by NSF, and also our lab is a member of the DNS Storage Alliance. Okay, thank you. Any questions?
Couple of questions. The first one was your AA break. One of the problems, as you mentioned, with the non-homocolumnar problem, which is mainly the fact that, especially in the sequencing side, not more on the synthesis side, but more on the sequencing side when you read that. So what kind of issues do you see with the AA break being misconstrued as an A rather than an AA?
Okay, so the question is like, what is the difference between the barriers A and A by using this kind of barrier layers into the DNS storage, right? So first of all, because of the error propagation, so if we don't do the break or the barrier stuff, so the error will be propagated to the end of the DNS strings. And the reason we use A because it's really, so because of the rotation code, there's no like AA in the pattern. So we just use AA as a kind of the special, we know AA is a barrier. And if we just simply use an A there, so we don't know whether this A is caused by the substitution error or insertion error or deletion error, or maybe the regular payload data.
Yeah, sorry. My question, it was mainly the sequencing or readback problem when you have two data in a row. Maybe
Okay.
You might also can read it as one A.
Uh-huh.
Unless depending on the method you use to read that, quite a few, especially if you use a core technique to read or something, you will also take it as a single A, two A's.
Okay.
Is that part of your error number?
Okay. So I got your I got your question. So the question is like whether the A barriers can introduce some errors, probably because of the long homopolymer, right? So based on some research articles, so based on the current technology can recover the long homopolymer with 3 or 4 consecutive nucleotides. That means you can recover AAA or AAA, but I think about like 4 or 5, so it may introduce really high error rate. But below like 4 consecutive identical nucleotides is okay.
Yeah. And the last thing in the comment is based on what David was saying, that for astronomy, you really want high quality images. So maybe this is really applicable to human visualized images, but not for machine visualized images, maybe not so applicable. Would you agree with that?
So basically, what is the scenarios of using approximate images, right? This is kind of your question. So I think this is also some reviewers ask us questions, what kind of scenario you want to use approximations of the storage system. So probably this is one scenario we can think about. So because machine learning so far it's become really, really popular, and we do have a lot of training data. And a lot of training data may belong to videos or images, right? So for the machine learning algorithm, sometimes we really don't need to have high resolutions of images. So because the machine learning just extracts some like the features of the images. So I think this is kind of one potential scenarios you want to use. And also there are some like preview scenarios try to preview the images rather than load the whole data out. And then I think this is also another scenario you can use a so-called approximate DNS storage system or approximate storage system. But a great question, yeah. Any other question? If no, we are kind of, okay.
Sure. So following off on the astronomy stuff, so let's say you stored an image of the night sky on a specific day at a specific time. Then let's say 900 years later, you're like, what this star here? So could you actually do some random readout afterwards? So like, for example, you look at the low resolution image, you're like, okay, here's like the area we should be looking for the star, and then do selective sequencing specifically in that area to just get the really high resolution image of like that little bit of area you wanted to see.
So your question is like, could we do the random access of the one specific part of the images, right? So I think in my talk here, so there's some works working on the random access of the DNA storage. So in general, we do have primers. So we do use different primers as an indicator or as an indexing to indicate, okay, this is a kind of one specific DNA strings we want to access. And also inside of DNA string, we do have internal index to indicate, for example, this is the first row of the images, this is second rows of images. But of course, you do need to have some metadata to store all those information. For example, you may have some metadata like this one specific primer, like ATCG, blah, 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 pointing to some, maybe one file, like file 1 or image 1. And then for the image 1, you go to the maybe specific internal index to get the corresponding, maybe the part of the images. So this is kind of my answer. But we do have limited number of primer, so the scalabilities of this kind of random access is kind of not good enough, I would say. Yeah. Great question. Yeah, thank you. Okay, thank you guys. Yeah.